Friday we talked about charged particles in electric fields. Now, there's certain things in physics that are just higher level thinking. There's just certain things that we've got to think really, really hard about. There's certain things, however, that are automatic. Now, I'm not suggesting the solutions to these problems that we're working on are automatic, but I am suggesting to you that what to do in these problems should be automatic. When we see a charged particle speeding up, we should automatically think that's like a car going down a hill. Let's do conservation of energy, like that car going down a hill. When we see a charged particle slowing down, we should automatically think that's like a car going up the hill. Just automatically. Now, that doesn't make the question easy necessarily, but it does give us a place every single time. It gives us a place to start. All right? Now, if we have a charged particle speeding up, again, picture it like the car going down the hill. We will solve the problem using an EI equals EF analysis, conservation of energy, right? What kind of energy must the car have at the top of the hill? It will always have this, Tanner, at the top of the hill. Potential energy, right? Now, the only difference here is that we're not going to call it potential MGH, we're going to call it potential QV, not QE. Remember, QE is electric force. QV rhymes with QE, but it's completely different. This is potential energy. Okay, electric force versus electric energy. Potential energy is QV. That just replaces the MGH. Now, we might also have at the beginning of this problem where it's speeding up, kinetic energy. But I'm going to star the kinetic energy because we don't necessarily have that. If the car is moving at the top of the hill, then we've got kinetic energy. If it's not, then we don't have kinetic energy. We'll always start with potential though. Maybe kinetic as well, but for sure potential energy. Now, at the end of the problem, after the car has sped up, picture the car going down the hill. After the car has sped up, will we still have potential energy?
Yes.
Who said it depends? Okay, it depends. If we're at the bottom of the hill, then the answer is no, we won't have potential energy. If we're partway down the hill, then we will have potential energy. So we might have potential energy at the end of the problem, except it's QV potential, not MGH potential, right? We might have potential energy at the end of the problem, but we might not. We will have kinetic energy at the end of the problem, 1F mvf squared. So the starred ones are maybes, depending upon what the scenario is. Okay, the unstarred ones, the ones that I have circled here, are for sure. We will always have potential converted to kinetic. We will always lose potential, gain kinetic. The total amount of energy will always remain the same. We will sometimes have kinetic at the beginning, and we'll sometimes have potential at the end. Now, some people, like me, when we're solving these problems, I like to put only the equations that we're using. And so if I'm starting off at rest at the top of the hill, or starting a charged particle starting off at rest, I don't even put in the equation 1F mv squared. But some people like to write it out like this every single time and then just cross off what they're not using. Whatever works for you is what you should do there. Either write down just the equations you need, or write down everything and then just scratch out what you don't use. I don't really care. Was there a hand up over here somewhere? Nope. All right. What about when the charged particle is speeding up? Sorry, it's slowing down, I should say. What about when the charged particle is slowing down? Go ahead, Tanner. Yeah, that's like a car going up the hill. And we should always, every single time, think of it like that, automatically. There's more to do. There's more to think about after we automatically do that. But at least it gives us a place, all of us a place, every single time to start. If a car is at the bottom of the hill, going up the hill, it slows down. It must, at the bottom of the hill, have, as you said, kinetic energy. It must have kinetic energy. Does it have potential energy at the bottom of the hill? If we're starting at the bottom, we would typically say no. You could say that it has potential if, depending upon where you define the bottom of the hill to be, though, right? So I'm going to put in an MGH there. Sorry, not MGH, but QV. But we'll star that. Normally in these situations where it's slowing down, we're not going to start with potential energy, but it could be, depending upon where you define your starting point to be. We'll always have kinetic though. At the end of the problem, when it's slowing down, do we still have kinetic at the end of the problem after it's slowed down? Maybe. Depends upon how much it's slowed down. If it's stopped, we don't. But if it's just slowing down to a certain speed, we do. Car goes to the top of a hill. Is it always stopping when it reaches the top of the hill? No, sometimes it does. Not always. If it doesn't stop, if it's still moving, then we'll have kinetic energy at the end of the problem. But we'll star that one because that's not always there, just sometimes. We will always, at the end of a problem where it's slowing down, picture the car going up the hill, we will always have at the top of the hill what kind of energy? Potential. Except we're not going to call it MGH potential, we're going to call it QV potential. Good? Again, some people might just X out the QV and the 1F mv squared if they're not there. Some people might write them in and X them out. Some people may just avoid writing them in to begin with, depending upon what types you have. These types, the starred ones will sometimes be there. The circled ones will always be there. The conversion taking place here is not potential to kinetic like it was when it was speeding up. Again, picture the car going up the hill. We're converting kinetic to potential. The total amount of energy, once again, will remain the same. Does that make sense? Okay. Let's take a look at worksheet number 9 that we had today. Our homework on this page was 3 questions, 1, 3, and 5. I want to go over question number 5 here. The toughest of the 3 for sure. It says a potential difference of 100 volts exists between 2 parallel plates that are 16 centimeters apart. And the electron begins at rest at one plate and accelerates toward the second plate. Okay, speeding up or slowing down? Speeding up. That's every time, automatically. Just like when we say force time graph, we automatically think impulse. Like just like when we see a funny angle, we automatically think, I don't like funny angles, take it off to the side. Okay, every time we see a charged particle speeding up, we automatically think that's like a car going down the hill, conservation of energy. So let's set that up that way. Okay, EI is equal to EF. This electron, this car, I should say, begins at rest. Does it have potential energy, kinetic energy at the beginning of the problem, Tanner? No, it doesn't. Does it have potential energy? Yes, it does. But not MGH potential, right? It's QV potential. Kelton, question?
Is it possible for electrons to get rest?
That's a good question. That's a good question. Let's say yes. That's a good question, though. Now, we're talking about a car here, aren't we? The car is going down the hill. It's not all the way down the hill, right? It's a 16 centimeter high hill. How far has it gone down? No, 4 centimeters. If I was solving this truly as a car going down the hill, and it went a quarter of the way down, then I would say my final height was 3/4 of my initial height, correct? That's what's happened here, right? It's gone 4 out of 16 centimeters across the plates. So it's got 3/4 remaining. Does that make sense? Well, I'm not going to put the final potential is 12. I'm going to say the final potential is 75, right? It's gone a quarter of the way down. It started off with potential, QV, where this is 100. It ends off with potential, where this is 75. I've got 3/4 of the gap yet to cross. I've got 3/4 of the initial potential yet to cross. So if I started with a potential of 100, now I've got, when I'm a quarter of the way across, 75 potential yet to go across. Now, of course, I'm looking for the speed of it. Clearly, it's speeding up. So we're solving for the F here. Make sense? Okay, let's sub in some numbers here. It is an electron, 1.6 times 10 to the minus 19. My initial potential is 100. Again, 1.6 times 10 to the minus 19 times my final potential, which is 75, times the mass, which is on your data sheet, times VF squared. So what I want you to do is get this number, take it over by subtracting, then times it by 2, divide it by 9.11. Let's go through that math just to make sure that you're okay with that. What do we got here? 1.6 times 10 to the minus 19 times 100. Okay, there's the left side. Now let's subtract from that. Use some brackets here. 1.6 times 10 to the minus 19 times 75. Now let's times it by 2, or you could divide by 0.5. And then let's divide by 9.11. And then what do I have left? What do I got to do now? Square root it, yeah. We square root that, and we end up getting 2.9633 times 10 to the 6. Well, we're going to round that to, how many digits should we round that to? 3 digits? 2.96 times 10 to the 6 meters per second? Is that okay? Parker's got his hand up. I think I know what question he's going to ask. I'm going to say it, and then you tell me if it's a question that I'm predicting you're going to ask.
Well, I think you know what.
Yeah, that's why I said I think I know what you're going to say. Yeah. We defined the initial potential here as 100, and the final potential is 75, right? What else could we have done here to maybe shorten this up a little bit? Is that what you were going to ask? Okay. What's the answer to the question?
You can just say equal to 0.5. That's all.
So my initial potential could be 25, and if I did that, my final potential would be 0, right? What matters here is this. The potential difference that I crossed is 25. If the total potential difference is 100, and I crossed a quarter of the way, then the potential difference that I crossed is 25. The potential difference is 25. So I can make my initial potential 100, my final is 75. I could have made my initial potential 25, my final would be 0. I could have made my initial potential 57. I'm not sure why you would have done that, but we could have done that. What would my final have been? 22. My final potential has to be 25 less than my initial potential. Does that make sense? The total potential difference is 100. I've gone a quarter of the way across. The potential difference that I've got to use here is 25. Whether it's 175 as I did here, or 25 and 0, which is the other logical one, doesn't really matter. Okay? How many people did do it this way? Or more or less this way? How many people did kind of catch that and did it the other way, shortened it up a little bit and said 25 and 0? You get the same answer, right? Go figure. Okay, let's take a look at question B. Question B, this time we've gone 8 centimeters across. We're still speeding up, so we're still going to say EI is equal to EF. We're going to say QV still equals, do we still have potential energy at the end of this problem? Depends on how we do it, right? If we do it this way, same way as we did here, then yes. If we do it Parker's way, then no, right? What would the initial potential be if we do it this way? What would the initial potential be here, Parker? 100. Yeah, what would the final potential be? 50, right? If we did it Parker's way, then we could say the initial potential is 50 and the final potential is 0. Doesn't really matter as long as the difference is 50 because we've crossed 50% of the way. Good? Okay, so we're going to say, this is the same idea, right? Except this is going to be 100, This is going to be 50. You're going to rearrange that the same way. You're going to solve for VF here. Would you expect that number to be bigger or smaller than 2.96 times 10 to the 6? Bigger, yeah. We're going to say 4.19 times 10 to the 6 meters per second is our answer there. Seem like a reasonable answer? First of all, we usually, in questions like this, tend to get somewhere in the 10 to the 5, 10 to the 6 meters per second speed range. Not necessarily, but usually. 10 to the 5, 10 to the 6. Here's my first indication that I'm on the right track here. Secondly, I got a number here that's a little bit faster than the first one. That seem reasonable? Should be faster, right? Because I've gone halfway across now, as opposed to a quarter of the way across. Yep.
So that is the velocity?
That's the speed, yeah, the speed.
Okay. Wait. Oh, it's not faster than light?
No, the speed of light is 3 times 10 to the 8. Yeah, you're right, you can't be faster than the speed of light. If you got 4.19 times 10 to the 8, you've made a mistake. Okay. Now, question C. This is probably the easiest of the three. Once again, we're speeding up. Once again, we're starting with potential difference. We do every time we speed up, right? Car at the top of the hill always has potential. What kind do we have at the end of the problem? If we've gone all the way across the 100 volts, we're at the bottom of the hill now, right? So we're going to say we have just kinetic energy. Here we're going to say 1.6 times 10 to the negative 19 times 100. My initial potential is 100. My final potential is 0 because I'm at the bottom of the hill. Solve for VF in this case, and we end up getting 5.93 times 10 to the 6 meters per second. Is that a reasonable number? 10 to the 5, 10 to the 6, yep. A little bit bigger than VF when we went halfway across, yep. Seems like a reasonable number to me, yep. All right, I would like you guys now, just for a little bit more practice yourself at this, to go back and take a look at question number 4 that was not assigned for homework. There's a proton, watch that, right? We often use an electron, and we get in the habit of using the data for an electron, okay? RTQ, ATQ, right? Read the question, answer the question. This is a proton, started from this speed to this speed. What potential difference required to do this? That's like a car going up or down? Down a hill. It's speeding up, right? So your car going down a hill. Automatically, we want to think that. Okay, take a look at that, and then in a couple minutes, we'll go over it as a group. All right, everyone, this question says a proton is accelerated from a speed of 5 times 10 to the 4 to 5 times 10 to the 6. What's the potential difference required to do this? Even though this question looks a little bit different, gave people a little bit of trouble in some cases, this is charged particles speeding up. Automatically, we're thinking it's like a car going down a hill. Automatically. We don't have to know how to solve this question. We have to know how to start this question. And when we have a car going down a hill, which is like what this is, we say EI is equal to EF. At the top of the hill, what kind of energy must the car have? Otherwise, it ain't going to speed up. Potential energy, right? But we're going to make it QV potential rather than 1/2 mv squared. Rather than MGH potential, right? Does it start with kinetic energy as well? Is this car moving, Alex, at the beginning of this problem? Yes, it is. At the top of the hill, this car is moving, in fact, pretty fast, 5 times 10 to the 4 meters per second. So we're going to start off with potential and kinetic energy. Now, what type of energy does it have at the end of this problem? Kinetic energy, right? We're going to say 1/2 mvf squared. Now, some of you say, well, how do we know if it has potential energy? How do we know it's all the way down the hill? Well, we don't. We don't. But we're going to define the final potential as 0. Whatever we get for the initial potential will therefore be the potential difference, right? Let's say the answer to the potential difference, which is what we're looking for, is 30 volts here. I'm making that number up right now, okay? But let's say it's 30 volts. If we set the final potential equal to 10, what would we get for VI? 40. And the difference is 30. It makes more sense, doesn't it, to set the final equal to 0 and get an initial of 30? But it's the same thing, right? So we can arbitrarily make the final whatever we want. I'm choosing to make it 0 because it's convenient to make it 0, and we can do that. Now, some of you are saying, oh, let's subtract the speeds and then square it. You cannot do that. The only time you can subtract variables like that is if they're not squared, if it's a linear relationship. Okay, if it was potential difference, for instance, QV, we can do that, right? But if it's speed, where it's 1/2 mv squared, you cannot do that. So let's just sub your numbers in here and see what we get. Proton is 1.6 times 10 to the minus 19. The initial potential, we're really looking for the potential difference, but since we're setting VF equal to 0, then that's really what we're looking for, right? The mass is 1.67 times 10 to the minus 27. The initial speed is 5 times 10 to the 4. Don't forget to square that. 1.67 again, times 10 to the minus 27. If you try subtracting the speeds and then subbing it into 1/2 mv squared, it will not work. You're going to get an answer that's close, actually, but it's wrong. I think it's 1.27 or something like that if you subtract the speeds, rather than 1.30. So close, but doesn't count. Get this number. Get this number. Take this number over to that side by subtracting, yeah, and then divide by 1.6. And I think our final answer works out to be 1.30 times 10 to the 5, is it? 1.3730 times 10 to the 5 volts. Does that make sense? Yep.
So no matter what, like you could have chosen to set the volts to anything. Or
Yes.
VI to anything.
No, you could have chosen to set VF to anything. Okay. It's like, here, let's go back to the analogy again for a second. Okay, here's my hill. Okay, we're looking for the height of this hill. Okay, we're looking for the height. So typically we'd set HF equal to 0, right? And we'd be solving for HI here, right? Make sense? Okay. We could have said, oh, wait a second, there's more to it. And this is what we're setting equal to 0. So this point right here, our final height is 10. Well, this is, let's say, a height of 30 meters one way or the other. If we set this equal to 10 right here, then our initial height will be 40. If we set this equal to 0, then our initial height will be 30. Any way we look at it, the difference in height is 30 meters. And that's what we're looking for in these questions, is the potential difference. That make sense?
Yeah.
So yes, we could have set our final equal to whatever we wanted, but it's usually convenient, not 100% of the time, but it's usually more convenient to set it equal to 0. Okay? That make sense, everyone? Okay, I want to do one more quick example with you, and then we'll give you a break, okay? The next example with you, that I want to do with you, is on your sheet. Here's the example. An electron is released in the electric field moving at a speed of 5 times 10 to the 6 meters per second in the direction of the field. Determine the potential difference required to stop the electron. Okay. Clearly, when it's saying stop the electron, we have a charged particle slowing down. That's like a car going up a hill. But the point that I want to make with this is this. An electron is released, moving in the direction of the field. So the field is in black here. The electron is moving in the direction of the field. Whether it's moving in the direction of the field or not, which way is the force on this electron? A positive particle experiences a force with the field. Are you sure? I'm positive. A negative particle experiences a force opposite to the field. So if it's moving to the right and experiences a force to the left, it is slowing down. Sometimes we're given an indication like this, right? Stop the electron. Okay, it's got to be slowing down, right? But sometimes you've got to take your hint from this. It's a negative that experiences a force opposite to the way that it's moving, then it's going to be slowing down. So for this one, it's our car at the bottom of the hill. EI is equal to EF. Car at the bottom of the hill is moving. Better be moving, otherwise it isn't going to go up the hill. Right? No gas, ran out of gas, just coasting now, just rolling. Now, when it reaches the top of the hill, sometimes it will be moving still. But in this case, it's not, because we're looking for the potential difference required to stop the electron. So it's only going to have potential at the top of the hill, but it's not MGH potential, it's QV potential. Good. We're looking for, well, really we're looking for the potential difference, but we defined the initial potential as 0, so the final potential will be the same as the change in potential difference. Could we have defined, for whatever reason, the initial potential as 10? Yes. We would have found our final potential to be 10 more than what it is here, though. Yep.
It says electrons release the field.
Yep.
They need to speed in the direction of the field.
Yeah.
So if it's moving in the direction of the field, it's the direction of the field.
No, it's moving with the field. Okay. Because of its inertia, it's moving with the field. Okay. The force is opposite to the field, though. We can make like I can climb a ladder and go against gravity field, right? Be moving against gravity field, or I can jump off the ladder and go with the gravitational field. Okay. In either case, whether I'm going up the ladder or down the ladder, the force is downward. So here in this case, this charged particle could be moving with the field, it could be moving against the field. In this case, it's moving with the field. The force is, in either case, opposite to that. So if this question started off as saying it's moving opposite to the field, then we'd be going with the force, and it would be speeding up in that case. So that would be a car going down the hill now. Does that make sense? Yep, go ahead.
Is this one of those situations where the electrons make that parabola we talked about? Or is that...
No. Let me just finish this, and then I'll answer the question. It's a good question. So listen, guys, we'd solve for VF there, and I can't remember what that would should be, but that's a pretty easy one to solve for, right? Okay. Let's say we got 20. Okay, let's say the answer is 20. If the answer is 20, that would be our potential difference, because we assumed VI was 0. If we assumed VI was 10, then we would have got 30 for VF. If we assumed VI was 15, we would have gotten 35 for VF. We get 20 more for VF than we get for VI. Therefore, the potential difference is 20. Makes sense to go 0 and 20, though, or whatever the number worked out to be, right? Now, I'll answer your question in just a second here, okay? Back to yours now. Hey, you said, is this one of those parabola things? No, this is not one of those parabola things, but it's close. If the electric field is this way, okay, the charged particle, the negatively charged particle, is moving to the right. It experiences a force to the left. That will simply cause the charged particle to continue moving in a straight line to the right, but slow down. Now, at some point, it will stop and switch direction, but it's still going to be along that same plane. That's not a parabola, that's just a straight line. If, however, you had an electric field going this way, and the charged particle was moving through it to the right, the electric force on this one is upward, opposite to the field. That's when we have this charged particle moving in a parabola. Does it make sense? Okay. Braden. Okay, good. Yep. If you graph, well, it depends on which speed you graph. If you graph the, if you graph velocity versus time, it would not be a parabola in either case for x or y. If you graph the position versus time, its horizontal position versus time would be a straight line, because it would be moving at a constant speed. But its vertical position versus time, in the second case here, its vertical position versus time would be a parabola. Does that make sense? It's projectile motion, right? Remember in physics 20, projectile motion. Okay, that would look like this, dx versus t. dy versus t would be a parabola. But if you were to plot velocity versus time, that would be a straight horizontal line because it's constant velocity horizontally. This is, again, for the second situation here. Okay. Velocity versus time here would be a straight line because it would be a constant acceleration. For the first one, what would we get here? Yeah, for the first one, for the x component, for speed versus time, is it? That would be a straight line sloping downwards because it's a constant acceleration or constant deceleration. No, because it's a constant deceleration. But the vertical, of course, there is no vertical, so it would just be right here, right? The position would, yes. The position would be, yeah. In a parabola, it's like when you're plotting y versus x and get a parabola, in the context of something physical like this, it's position that's on the y-axis, not velocity. It's on the y-axis. Okay, I'm going to have you guys look at, on your worksheet, question number 6 for homework. But you can take a break right now if you want for 4 minutes. Remember, the question number 6 is going to be a homework question for you.